Okay, so today we have Dr. Samuel Ma from College Station here with us today. And Dr. Ma is an associate professor in the departments of civil and environmental engineering, again, at Texas A&M College Station, and a good friend of mine. He has a PhD from Missouri University of Science and Technology in, I believe it's 2004. He's definitely a very prolific researcher with well over 100 publications by now. And he does a lot of research on, trying to understand the fate transport and potential impact of what we call emergent contaminants. That also includes microplastics and per and polyfluoroalkyl substances, or PFAS. So he has done numerous different technologies, including plant uptake in transformation of a range of environmental pollutants, and also, I guess, more advanced molecular level biochar catalyst under his portfolio. I think I just covered some of the research topics that he has been doing. And so I think it's best to just hand it over to Dr. Ma and let me introduce more about his research. Then?
Okay. Oh, great. So thank you for the opportunity to share my research with you all. Let me first make this presentation mode. Okay. Here we go. So yeah, today I will share a recent research we have done in the lab, which is the degradation of PFOA by a metal organic framework. So PFOA is one of the PFAS compounds, right? And PFAS is very prevalent. So today, if you look around the products you use, for example, your pots in the kitchen, you probably see a sort of a black coatings, the water preventing coatings, and so on and so forth. They all contain PFAS. Okay, so there are different products, but what they are in common is they all contain some PFAS compounds. And those compounds are critical for those products to function as what we are supposed to. But there was a concern. The concern is that those PFAS compounds, while they can do a lot of wonderful things, if they are released to the environment, they could cause damage to the ecosystem. They could hurt humans. They could affect our, disrupt our hormone systems. They can even cause cancer. So that is a concern. So because of that, the EPA very recently, by recently I mean this June, this summer, provided an updated advisory level for some of the PFAS compounds. So for example, if you look at the screen, you can see that the PFOA, the advisory level is 0.004 ppt, which is below the detection limit of any technology we have. So basically, what that says is that we don't want any PFOA in our water. The same thing is true for PFOS. The current advisory level is 0.02 ppt. So that's also below the detection limit. And those two compounds has been on the list of EPA for a while, for a few years. But this year, they added two more to the list. One is called HPFO or GenX, and the other one is PBS, and their reference levels are slightly higher, 10 ppt and 2 ppb. Okay, so and in addition to that advisory level, so when the EPA has an advisory level for certain chemicals, so that's what they suggest, that we should try to keep the contaminants at a lower level than what they suggest. But if you break that, EPA is not going to do anything. So this means that it's not enforceable. But the EPA does consider to have enforceable standards for PFOA and PFOS. We don't know where the level is yet. Okay, so but that's where this direction is going. In addition to that, EPA is now collecting more toxic data for a bunch of other PFAS compounds, including PFBA, PFBS, and so on and so forth. So those names are probably strange to you. So we will get there. We'll talk a little bit more about the PFAS. Okay. So first of all, For some of you who are not very familiar with PFAS, what are those PFOA and PFOS and so on and so forth? Okay, so here are the molecular structures of the compounds. This is PFOA, perfluorooctanoic acid. Octo means 8, so if you count the numbers of carbon, they have 8 carbon, and all of the carbon are replaced, the hydrogen attached to that are replaced by fluorine. And then there's a carboxylic functional group. So PFOS is similar, but the functional group is a sulfonic acid functional group rather than carbonic acid functional group. Okay, so each of them have 8 carbon, and we call the PFAS compounds which has 8 or more carbons long chain carbons. Long chain carbons are toxic, as we said in the last slide, right? They are there's a whole lot of health concerns. Therefore, the industry is gradually staying away from these compounds and find replacing compounds which are hopefully less toxic. And for PFOA, the replacement compound is this one here, HFPO or DA, or Xingmao. Mostly, it's a salt form of that compound. And for PFOS, the replacing compound is sorry, this is not PFOS, this is PFBS, 4 carbon. So if you compare the differences, is that replacement compounds are relatively shorter, and some of them have this ether compound that makes them more water soluble and also more hydrophilic. And what that does is that if we do take those compounds into our body, for the long chain compounds, they would probably absorbed by the lipid in our cells that will stay in our body longer. So those compounds would stay relatively shorter. And the hope is that when you can just stay our body later in a short time, so they will be less toxic. So that's the reason why we are replacing those long chain compounds with short chain compounds. Okay. But as you have seen that the EPA is not only interested in those 4 compounds, they're interested in a lot more. And in fact, the PFAS, right, is a very large group of compounds. How many compounds are exactly are we talking about? So at least 4,700 of them. Okay, so PFAS is a very huge group of compounds. And the full name of that is per and polyfluoroalkyl substances. So in the previous slides, when you look at the name of the compounds, you all see per, right? So, but then what is the poly and what's the per? So basically per means that for every carbon. Okay, so if you look at every carbon, there's no other elements. So they are all either attached with another carbon or fluorine. Okay, and the poly basically means that you have some carbon which are the hydrogen is replaced by fluorine, but some of them still can connect with other atoms such as chlorine or hydrogen and so on and so forth. So meaning that not all of the carbon is connected with fluorine. So those are the poly. So those are 2 big groups of compounds. And in addition to those individual compounds, some of the PFAS compounds, they are behaving like a monomers, and giving them certain conditions, they could link together to form very large materials or polymers, so that you have this polymer materials and the non-polymer PFAS. Okay, and in general, the polymeric PFAS are not a major concern because they are big, and the chances for us to take in through food or through water is relatively small. But those non-polymer PFAS, they are in water, they are in the environment, they're in soil, widespread. So the chance for us to take them in is high. And so that's what it really, from a health perspective, people are more concerned about, okay? And so under the polyfluoroalkyl substances, based on the functional groups, you could have different types of PFASs. And the same thing is true for perfluoroalkyl substances based on the functional groups. At least you have seen that some of them are having a carboxylic functional group. So those are called perfluoroalkyl carboxylic acids, and some of them have sulfonic acids. functional group. Others could have sulfamides, amides, and so on and so forth. So based on the different functional groups that it attached at the end of the compound, you could have different groups of the PFAS. And because of those different functional groups, right? So when you probably have known that if you add some carboxylic acid in water, they will dissociate, right? So a lot of those functional groups dissociate, or they can accept the protons and so on and so forth, and so on and so forth. For example, carbonic acid could dissociate to form bicarbonate and then carbonate. If you have this amine group, they could take in a proton and so on and so forth. Because of that, the PFAS, okay, so in our water, it's often would have charges. If they dissociate, lose some protons, then they will carry some negative charges. If they take in protons, they could carry positive charges. Apparently, some of them, for example, if they have just alcohol functional group, then they will maintain as neutral. So based on this here, what you can see is that PFAS is really complicated. So it has different molecular structures, and the chains, the carbon chains could have different numbers. So you could have different size of that. Some are bigger, some are small. And also based on the functional groups, you could have different charges. Okay, so it's really a very diverse group of the PFAS compounds. So here are additional examples of the PFAS. So for example, some of them could have, say, alcohol as a functional group. Some of them in the molecule which contains not only fluorine, could have chlorine and so on and so forth. So really, the structure is very diverse. And for some of you who are interested in PFAS, right? So what I would recommend you to do is to read this paper here. So this is a review paper published in Science last year. And this paper was authored by a group from North Carolina State University. So they are really the first group of researchers who brought attention to this emergent group of contaminants. So a fairly decent review paper. So if you're interested, that's where you would be able to learn a lot more information about the PFAS, okay? So, so now, because PFAS, whether we like it or not, it's already widespread in the environment, in the water, in soil, in plants, in food. So now the question is not only that what PFAS are in and how do they move, we are still interested in that, but more importantly though, we have already some PFAS in water. How do we remove them, right? So currently there are two strategies for us to follow in terms of removing PFAS from water. So one type of technologies or one group of them is called non-destructive technologies. Basically, what we are trying to do is to physically remove PFAS from water. And the way we can do that is through adsorption, for example, or ion exchange. So that provides larger surface areas so that the PFAS in water could adsorb and condense in solid. Therefore, you have less PFAS in water. Or you can pass the water through membrane. And you know that I heard that Dr. Dan's teaching desalination, right? So you must talk about desalination, reverse osmosis, nanofiltration, and so on and so forth. Based on the pore size, you can remove very small atoms, right? Even some ions. So PFAS will be much bigger. Therefore, the membrane technology would be fairly effective to remove PFAS. Okay, but there's a problem. The problem is that we only physically transfer PFAS from the liquid phase to the solid phase or to the concentrate of the filtration process. So after we condense them, we still need to treat them, right? We need to post-treatment the spent materials, and that could be a problem. So the good thing, so far we haven't had any really environmental sustainable and very effective technology that could treat those PFAS spent materials very effectively. But only very recently, though, a paper again published on Science by people from Northwestern University. What they said is that they did find some ways that they could, with relatively low energy consumption, they could mineralize perfluorocarboxylic acids, not all PFAS, just a group of them, under certain conditions, even at very high concentrations, as what you would expect to see in the spent materials of adsorption. So that seems promising. Nothing has been tested in the field side yet. So this paper just came out this year or this summer, either June or July or August. So very new. So if you're interested, you can look at this paper. But so far, the questions remain that if we use physical technologies, the spent materials will something we still need to treat. So therefore, what we really prefer is we can develop some destructive technologies. We can break that, destroy the compounds, break that into something smaller, non-toxic, okay? And so far, there are a lot of approaches people have tried. For example, you can use thermal treatment. Basically, you heat it up to very high temperatures. You can use electrochemical treatments, irradiation-based treatments, or photocatalysis, or other catalytic processes, such as, let's see, what are the others? Either photocatalysis or electrocatalytic processes, right? Or use very high energy based technologies. So why do we need high energy to really break down PFAS? The reason is because that based on the molecular structure I have showed you, that those PFAS compounds has a lot of those CF bonds, right? And CF bonds happens to be the strongest single bond in chemistry we have found. So the bond energy is 544 kilojoule per mole. So that means that if we want to break that, we will need to have a very high energy to really break this. So that's why no matter what the technology you use, the energy demand is very high. And those technologies worked in the lab, right? But in the field, how do you create either say, for example, gamma irradiation? So that could be probably dangerous. How do you heat up the water? If you imagine the drinking water treatment process, which treats, say, 100 gallon or 1 million gallon per day, right? So how do you treat the water up to 100 degrees? So that will be very unlikely because I will use a whole lot of energy. So, so that's the problem. So what can we do? So what can we do is, so our approach is that if we want to break PFAS, right, we do need to provide the energy. So can we search for some more sustainable energy, such as solar light? So because of that, so we came up with this idea that let's try photocatalysis, phototechnology, right? It is an energy source, more green and sustainable. So photocatalysis or photocatalytic technology is not new. So it has been used for many years, and a lot of those semiconductor metal oxide, for example, titanium oxide, zinc oxide, right? So it has been used for many years. So the problem for them is that, for one thing, the band gap of that is relatively high, so that if you want to use them for photocatalysis, you will have to create some UV light. The solar light, typical solar light we often see, will not work. So secondly, so because they are metals, so they are solids, so what really works for them is it's only on the surface, right? So, but there's another type of photocatalysis, which is a metal organic framework, is a porous material. So the advantage for that is that we can tune that so that it could respond potentially not only to UV light, but also to visible light. And another advantage we could imagine is that because it's porous materials, when you have porous materials, what that means is that you have a lot of specific surface area. It's not only on the surface, but inside the structures, right? So that means that PFAS could potentially adsorb on the surfaces. Therefore, you can quickly concentrate the PFAS and then degrade. So that would potentially improve the process, increase the kinetics. So therefore, we decided to try that out. And we have tried several MOFs. And today, what I'm going to focus on will be this one here. So MOF means metal organic frameworks. So basically it's a pore structure which has both organic links and also this metal clusters. So basically you have lots of metal clusters and then you link them together. And if you can make that relatively rigid, and then you create a 3D structure. So that's porous, adsorptive, but by tuning those, by really choosing either certain metals such as titanium or certain links, right? So you can make them both photo responsive. So both of them are, and so again today I will focus on this one here, the MIL 125. By the way, this MIL, if you look at the names of MOP, you always see some letters in the beginning. Those are pretty much the either universities or the places where they create this MOP structure. Okay, and this one here means that we have functionalized the organic links by attaching an amine group to it. So the work I'm going to share with you has just published recently in the Journal of American Chemical Society. And for some of you, again, if you are interested, you are welcome to read the paper and let me know if you have any questions. So, but basically the study, the object of the study was that we would like to explore just evaluate the feasibility of the photocatalytic MOF, in this case it's 125, to see whether that can be a sustainable photocatalyst for PFOA degradation. So we chose PFOA because PFOA, first of all, is one of the most common PFAS compounds. It has been on the AP list for a while, even though the production of the PFOA is pretty much stopped in the US. But because they are so stable, PFAS are called forever compounds. It means it's very difficult to break. So even after 20, 30 years, they remain in the environment. So they remain an issue for the water quality. So that's why we focus on PFOA in this study. So our next step, objective study, if we do see that MOF is working, so then how does that work? Right? What are the mechanisms? Who is responsible for breaking this PFAS, and what are the compounds? Are we going to break the PFAS to all the way down to, say, carbon dioxide, mineralize that, or we will produce a whole lot of other compounds that could be potentially a headache as well? So those are pretty much our objective. So here is our setup, right? So we basically mix the PFOA in water, add PFOA in water, and we mix that with a bunch of other chemicals. I will share that with you, and expose that to a light source, this mercury light source, and then we monitor the PFAS concentration change over time and see what happens. Okay, so one thing I want to mention is that in our system we add a glucose in the system. The glucose, we add that as a sacrificial reductant to quench these holes here. So what does that mean? So what that means is this, okay? So if you look at a semiconductor, the electrons are initially stay here, okay? Stay at this bottom here. So when we expose that to light, the light energy will energize electrons so that it will jump to a different level of the energy. Therefore, electrons gone, therefore you leave a positive hole, because in the beginning it's a neutral, right? So that you have this electron hole here. And unfortunately though, the energy passes very fast, and once the energy is jumped here, it has a tendency to come back. Just when you throw a ball to the air, because of the gravity potential, it quickly drops back. The same is true, the electron potential will take that back here. And when that happens, then this will not work for us. Okay, so what we want to do is we want them to separate. so that you have a hole here. So when you have a hole, what the hole can do is, because now it carries a positive charge, right? So it has a tendency to grab electrons from whatever they see. Therefore, if you have a chemical, right, if it has an electron which can lose that, then you can lose the electron. And when it's lose the electron, this chemical is oxidized. Okay, so that's how this can oxidize this chemical. But this electron here, if you have a chemical which could take this electron, then this chemical would be reduced. So that photo catalyst, you can do either oxidize the chemical or reducing the chemical, depends on which one do you really want to use. So in our case, we would like to use the electron to reduce that. And the reason is based on our experience that we have studied the current compounds for many years. And for current compounds, oxidation does not really work. You need to reduce that to dechlorinate those compounds. The same is true for those PFAS compounds. If you want to break them, you want to defluorinate those fluorines, and the reduction will be a much better likely technology to remove fluorine from the compounds than oxidation. So therefore, we add a glucose. So the glucose is a reducing compound. Therefore, quickly that will lose an electron, and that will quench this hole. When this hole is quenched, now there's nothing to attract the electrons, right? So initially you have a hole, you have a electron, so positive negative charge, so they attract each other. So now once this combines with electrons from other sources, now this electron would more likely to stay here and to reduce other compounds. Okay, so that's the reason. And that turned out to be really necessary. So if you look at this PFOA change over time, or we expose or combine or mix the PFOA with different chemicals and expose them to light or different conditions. And what you can see is that light itself does not really do much. When you just add a MOF itself in the dark or even expose the light, and even though it's photocatalytic, we know that, and it does not really do much because that combination of electron hole is very fast, okay? And glucose itself doesn't do much, but when we add glucose MOF and the light together, it really does its wonder. See, in 24 hours, everything's gone. But in all other treatments, you remove a tiny bit of that PFAS, but very unimpressive. Okay, so those components, we need MOF, we need the photocatalyst, but we also need the quencher and the light. These are all necessary conditions. When we combine them all together, we can effectively remove PFOA. So knowing that, so our next step is how does that work, right? So first of all, we confirm that the kinetics, we want to see, okay, 24 hours, they are all gone, right? So how fast will be gone? So we let it run for 24 hours and then try the different concentrations of glucose. And one thing you can see is that the removal kinetics or the rate of PFOA degradation depends on the amount of the glucose. Okay, so clearly this shows that the glucose indeed play a role in our system, and higher concentration will lead to faster PFOA, hopefully degradation removal. So, but at this point, people could still ask you, in the system, indeed, this is you removed quite a bit of almost 100% of PFOA, but do they are they really removed, degraded, or are they just adsorbed somewhere on the MOF? Okay, so one thing we have done is to confirm that PFOA is not only adsorbed on the surface, but also breakdown. We monitored the fluoride concentration in our system, and we can see that fluoride concentration increases over time, clearly, which shows that PFOA is degraded in the system. It's not only adsorbed. So that's exciting, right? Now, the question comes that, okay, so the system works. How does that work? So one question is, who or what in the system that causes the degradation of PFOA. So when we have a photocatalyst, okay, as what you have seen, that will have this hole here, and then have the electron. Because these are exposed to water and water have oxygen, right? So oxygen will, some of the oxygen will quickly react with this electrons to form this superoxide radical. So superoxide radical is a fairly reactive radical, right? It's the an oxidizing radical. For some of you, again, a lot of radicals are generally or radicals are in general always very reactive. Okay, the reason is because that to make the chemicals stable, what you want to do is you want your electrons, either you have 8 this stable electrons, right, or even 18 or 2, something like that. But when you have a radical, that means that one of those orbitals has only 1 electron, and so it's not stable. So more likely, more preferably for that chemical is let's grab an electron whenever we can get that, so that it will be more stable, right? So what that means is that the radicals are often fairly reactive. So the same is true for this hose here. When you have water, this hose could form this hydroxyl radical. And some of you might know that hydroxyl radical is very reactive, right? So basically in our system, we have many things. We have this more oxidizing holes and the hydroxyl radicals, and we also have some reducing electrons. So who is responsible for the degradation of PFOA? So there are different approaches to answer this question. One simple approach is that let's use some quantum study, right? Do some quantum study. What that means is that let's add some certain chemicals, which we call quanters. And the chemicals, what we add is that they are more reactive to those radicals or the species than the contaminants we're interested in. So that if whatever the chemicals or radicals is responsible for PFOA degradation, then because we have something which the radicals are more preferable to react, so they will be consumed by that quantum, therefore they will not react with PFOA, then you should see a decrease of the PFOA removal efficiency. Does that make sense to you all? So that's basically what that is, okay? So now we add 3 different types of quanchers. One's glucose that's naturally in our system, and so if you look at the red dots, so that's what we see. If we take away the glucose, we see those empty circles. So basically, you don't really remove much of the PFOA, right? So the quancher is necessary. So now if you add glucose and the SOD, and it was so SOD quenches this hydroxyl radical here. So basically, then there's even you take away all of this, there's essentially has no impact on PFOA removal. So what that means that the you could have those superoxide radicals in your system, but they don't really do much, right? In terms of the PFOA removal. And now we had added this silver nitrate. Silver nitrate is the quencher of these electrons. So before they start reacting with PFOA, you react with silver. So, and when we add that, indeed, we see a huge drop of the removal efficiency, big gap right here. So that really means is that electrons indeed plays a major role in PFOA removal, right? So, but they didn't really bring that all the way to here. So what happens? So even though you quantitate all of this, there's still some removal. And our hypothesis is that this hydroxyl radicals could potentially oxidize some of the PFOA, okay? So based on the quantum study, then our conclusion is that those 2 reactive species are pretty much what really makes the PFOA degrade. So is that true? So in general, in scientific study, the quantum is often considered as a first step to kind of screen that which radicals are more responsible, which reactive species are more responsible, but that cannot be used as a definitive evidence. The reason is because as the quanchers we add, so They could react with whatever you are interested in to kind of figure out whether they're responsible, but they could react with other species. So this is a very complicated chemistry involved, okay? So one thing people tend to do is that provide some direct evidence that those radicals are indeed in your system. And those are often, the information is often obtained from the electron paramagnetic resonance analysis. Okay, so the machine is something look like this here. You inject your samples here, and then you monitor the signals. And the signals output from that equipment is something look like this. Okay, so those peaks here give you the information what the radicals you have. So basically, based on what we have seen is that indeed we have seen in our system, we see hydroxide radical. So that's a indirect indication of these electrons, because electrons are very difficult to monitor directly, because that electron, as you know, they cannot stay in environment independent by themselves. They have to attach to some molecules. So in order to do this one, you would have to lower the temperature to really almost close to zero absolute temperature. So that will be challenging. So we didn't detect this, but we did detect the superoxide radical. So that is an indirect indication that we do have hydroxide or hydrated electrons in our system. And we do detect the hydroxyl radicals even with the quenchers of glucose and SOD. So what that means is that in our system, we have some of those hydroxyl radicals, and that's mainly from this incomplete quenching of holes. And the reason for the incomplete quenching is because that the mouth is a molecular structure, right? So some of those holes probably is inside of the pores, but when you add glucose, in order for glucose to diffuse into the pores, it takes time, and also you need to make sure the pore size is large enough for glucose to pass through. So because of that, the quenching is not 100% efficient. Therefore, you end up having some of these hydrated electrons, but also some of the hydroxyl radicals. And that turned out to be critical for the MOF to work. So that you will see in a moment. Okay, so after figuring out who is responsible for the PFAS degradation, right? So then we said, okay, what the PFAS has degraded into, what they have become. So this, in order to answer that question, what we have done is we did a target analysis for HPLC MS analysis, and we have identified a bunch of those metabolites. Okay, so if you look at the metabolites even closely, so on this column here, okay, on this column here, so they all have same 8 carbons, right? So the structure is very similar. So what the difference is that some of the fluorines now replaced by this hydrogen. So that's defluorination. So that's part of the source of the fluorines we have detected in our system. And there are another group of them have the same carbon, but kind of similar, right? And then if you look at this column here, so they have similar structure as PFOA. You have as head functional groups so there, but the carbon is becoming shorter and shorter. This have 8 carbon, have 7, 6, 5, 4, and 3 carbon. Okay, so those are the 2 types of the metabolites we have seen in our system. And what that really means is that in our system, this PFAS has been degraded through 2 passes. One is called chain shortening, and another one is called HF exchange. So those are 2 mechanisms are common. They have been reported in the literature. Okay, this is not something new we found. So, but then we are concerned about, interesting, how does this happen in our system? Okay, so in order to answer that question, we have done some DFT calculation. DST is called Downs functional theory calculation. So what that have done is that, so first of all, we said, okay, assuming that this is PFOA and based on the metabolites, what we have seen is that 2 steps or 2 approaches, 2 methods, which lead to the degradation is that either you cut the carboxylic group or you do this exchange, HF exchange. But when we did this calculation, though, what we found is that, this really doesn't work. because the energy requirement, if you do that, then the thermodynamically this does not make sense, because your product has higher energy, so this will not occur spontaneously unless you put up energy, right? You provide a lot of energy. So then what really happens? What happens is that we found that if you say, remember that our mouse system creates these hydrogen electrons, right? If we allow the electron to attach on the molecule to form a PFOS anion radical, and then suddenly the energy dropped to a much lower level. And now if you still do those two steps of carbon chain shortening or HF exchange, we found that the energy becomes favorable for both of them. Okay, for both of them. And apparently the HF would be a lot more favorable than that, but then still this happens. So I will explain in a moment that what happens here, so that even though see the energy here, the energy benefit is much smaller than the second step, which is HF exchange. This still happens, okay? But from this slide, though, what you can see, the message, take-home message is that hydrogen electrons is important, okay? What happens to the hydrogen electrons? Why the hydrogen electrons is important? So just very briefly, what that happens when you have the hydrogen electrons attached to that, it will cause this redistribution of electrons in the molecule, and the concentration of electrons, because of electrons are most condensed to here. So that's why it makes it a lot easier to cut this bond off. Okay. So that's what happens. So basically what we have seen is shown is that, so I will watch my time, so we still have time. These hydrogen electrons are important. Then how does that happen? So now what we have seen is that from this step, right, you could potentially go to the decarboxylation and HF exchange. So we did that, we calculated this direct decarboxylation, and our calculation shows that this does not really work well. So what really happens is that we found the carboxylation actually takes two steps. So this is what we have found in the first time. Instead of going one step decarboxylation, you would need to have to get rid of one oxygen first, and then this CO group in the second step. That will require you to have this hydronium in your water, which is the protons. And it happens that in our system, our pH is about 4 or 5, so that it has plenty of the protons to make this step occur. All right. So once that happens, then here we form this radical here, and that will need this hydroxyl radical to make this hydration process occur. So by doing that, you form this intermediate products, and from there, then you can go through the process as what has been reported in the literature, and all the way to another compound here. You end up having similar structures, but one carbon shorter. Okay, so the take-home message is that in order for this PFOA to decarboxylate and shorten itself, those two radicals or reactive species are necessary, and our system happens to have both of them. And in the HF exchange step, we also did some calculations, and which shows that the decarboxylation step will, or the HF exchange step will need to start from the first alpha carbon, and then move to this one here, and so on and so forth. So basically, the calculations give us the information that which fluorine is the most likely to replace, and we compare that with the chemicals we here, the chemicals the metabolites we detect, to see whether we can theoretically explain why we are seeing those somatic chemicals in our system. Okay, so basically this explains why we are seeing some of the metabolites we see. And also, one thing is that in the previous slides, I asked you that even though this is spontaneously favorable, but the energy benefit is much less than the next step. Well, why did this happen? The reason is because that if you take a two-step decarbonization, that will make the energy also favorable so that you can simultaneously in your system to have those two decarbonization and F exchange occur in the system, okay? So basically we found a pretty working well system. And so the next step people often are interested in the material side is that, okay, you got a good system. Will that last if you collect the materials and try it again? Can they still break down PFAS? So that's what we did. So after we finished one round of the study, we collected them off, and then we tried that again. Expose that to same concentration of PFOA and same conditions and monitor the PFOA concentration again over time for 3 times. And overall, MOF maintained its functionality, maintained its performance, right? Over the 3 cycles, you see a slight drop, but it's not anything major, right? You still removed quite an impressive amount of the PFOA. We characterized the structures before and after. This is an SE image showing that indeed after 3 cycles, you still maintain the crystal structures. Surface area didn't really change much. Crystal structure maintained, and the pore size distribution are also similar. So basically, what it says, the MOF structure is fairly stable, okay? So with that said, now I can wrap it up our study by concluding that we do see that MOF is fairly effective. And in our system, we have both reducing reactive species, which is a hydrated electron, and oxidizing species, which is a hydroxyl radical. So the combined performance or actions of those 2 reactive species lead to high removal of the PFOA in our system. So what that means that HF itself could be initiated by just hydrated electrons, but in order for us to have effective, efficient chain shortening, we must have both reactive species, right? And very encouragingly, this MOF also displayed fairly stable condition. You could use that multiple times, and that's great. So with that said, thank you all for the opportunity to share my research with you all. And I'd like to thank my students. Xingmao Wen is the one who actually have done most of the research, and he is now a postdoc at Georgia Tech. Angel is the one who did the simulation, and a lot of my collaborators in the Department of Chemistry and the School of Public Health here at Texas A&M, and apparently the funding sources for supporting the research. So with that said, so now we still have about 10 minutes. I'd happy to answer any questions you have. Okay, so thank you.
All right, thank you, Sam. Thank you, Dr. Ma. I'll probably classify this as a deep dive into the research world.
Okay.
I'll be honest. I don't think many students actually catch up with this. It's very, lots of chemistries and research.
Yeah, so I apologize if
I'm
I'm trying to just tell you the story doesn't get deep, but I apologize that I should have prepared slides.
No, that's fine. That's fine. I'm just saying that it complements to one of our previous speakers. I have Purushottam here like 2 weeks ago. So he talks about PFAS in terms of pilot and full scale studies. So he focused on ion exchange and carbon absorption for PFAS removal, whereas yours focused more on oxidative
degradation
situation.
Yeah.
So I am going to open up the floor if in case anybody has any questions. If not, I do have a couple questions myself.
Okay, I don't see a hand from Timothy.
Yeah, I'm also missing a couple of students.
Okay.
Anyone, any questions?
I would just like to make a comment. I mean, I do know that I did go into College Station for the REU program in 2021, and it was really more like a boot camp for 3 basic systems: septic tanks, aerobic treatment units, and ozone units. We knew that PFOS is an emerging contaminant. We never really went through those things, but we did see a device similar to what you were seeing, like in one of the labs, like outside of the Hope's lab,
Okay.
I believe. So I
Yeah.
do get the concept. I think it was more about a ionic ionic exchange, I believe.
Mhm.
Or maybe we have an e-beam facility here. So so there are many people studying PFAS. So we actually, at least on this campus, I know at least 3 groups are studying PFAS. So one's the e-beam. So that's a very energy intensive. There's another group of them are focused on more on the biological degradation. They are trying to create this superbugs that could potentially biologically degrade PFAS. So we are using chemical approach to break PFAS.
Okay, that sounds cool.
Yeah.
All right, thanks, Tim. Pablo?
Thank you, Dr. Dan. Dr. Ma, I would like to ask you, like, which volumes of water do you use for your study, and how large can your system treat water? Like, yeah, the volume, how large volume
Okay.
can be treated?
So, okay, very good question. So this study we used, I believe it's a maybe 200 milliliter tube, but we are actually in the process to do a sort of a pilot study. So now we have a scale that up to a few liters, and we are trying that. So if that works, then we could potentially hopefully further enlarge that. So far we have moved from a few hundred milliliter to several liter.
And time-wise, is going to take 72 hours. That's what I saw in your presentation.
Yeah. So now we have for the mouth, right? So we in the lab we saw about 24 hours. Apparently, for some of the training process, that time is too long. So we are working on to develop more efficient materials, so that could hopefully break down PFAS in much short time. I mean a few hours, hopefully a couple hours. That kind of similar to the retention time of water in the drinking water or wastewater system.
Thank you, Dr. Ma.
Okay, you're welcome.
Okay, so my question is probably more about the setting itself, more so than the mechanisms and reaction rate. So I guess the EPA advisory health advisory standard for total PFAS, including PFOA and PFAS and PFOS, is 70 parts per trillion, right? That's according to my understanding.
Right. So those are the old ones. So they have just updated that. So basically, so this one they just updated this June. So before that, that's the 70 ppt is for PFOA and PFOS. So they updated that. So what you can see is that as for this current advisory, the PFOA PS is much lower, and those are just sort of, I guess, still the test advisory, not certain, but for the interim standards, but for GENEX and the PFBS, so those are the final advisory levels. So basically for GENEX 10 ppt, this is 10 ppt, right? And for the other ones, 2000 ppt or 2 ppb for the PFBS.
PFBS, okay.
Yes.
Okay. So in your experience, you use PFOA as your test compounds.
Yeah.
So what was the concentration, the starting concentration of your test?
We started with 100 ppb.
100 ppb.
Yeah.
So which would be 100,000 ppt. parts per trillion.
Yeah, it's very high compared to what's the standard. But those are, we start use the 100 ppb. It's relatively high compared to water. So in the water, so some place you probably see several ppb. But what we want to do is we want to make sure that we can detect the PFAS,
Yes.
and especially those metabolites, right? So once they break down, we want to make sure we have enough those metabolites that we can detect.
Okay. No, I didn't think 100,000 ppt is too large, or 100 ppb is too large. I think those are probably in line with what we saw from the refinery wastewater. It's
okay.
several 100 ppb of PFOA. So
Okay.
it's probably realistic.
Realist. Okay, that's good.
So my other question is, using glucose as a reductive agent. So would adding glucose, other than, I guess, facilitating a reaction, would that create additional challenge as far as compromising the oxidative nature of the compound, of the what do you call it, the MOF?
Yes, so that's a very good question. So we have tried several different types of those sacrificial reductants. And so something we do is that, so in the real system, apparently we cannot dump a whole lot of glucose there, right? So, but in the real world though, the water contains a lot of reducing agents, which are the natural organic matter. So, so essentially, if you, so they are doing similar stuff, and we actually have data to show that if you use certain organic matter, so they can function just as glucose. So that's what really happens.
Okay.
Yeah.
I remember there's one slide that compares the different combination of I think MOF only, lights only, and glucose only in different combinations. So I'm curious about what happened if you go MOF with glucose, but with no lights. Would that still induce?
It will not work. No.
Will not work.
Light is needed. Right.
Okay.
Without light, you will not have the separation of the electron hole.
Okay, so MOF is essentially useless without light.
Yes.
Okay. So it has to be all three components, right? The
Yes.
MOF, glucose, and lights.
Yes.
So any two out of three combinations wouldn't have worked.
Wouldn't work, right?
Okay. All right. Questions, guys? Okay, so my other question, this is probably not relevant to the core of your research, but would you consider, or how would you comment on electrochemical processes for PFAS treatments versus I guess the photocatalytic oxidation process?
So the electrochemical, if you can break PFAS electrochemically, that would be better than photocatalysis, right? So because in the real world, the light is not that easy to use. So in fact, our lab, so we are working on electrocatalytic processes, and we, I think we have seen something interesting. So maybe in a few months, we would probably have some publications on that.
Okay, does that work? Any does the electrochemical process works?
So far we have, yeah. So we have some preliminary data which shows that actually the materials we newly developed worked very well. So I don't know the reason yet. So we are still trying to figure out the mechanism, but the kinetic is much faster than MOF.
Okay. Okay. All right. Sounds good.
Yeah.
Okay. Last chance questions. I think our time is up, but just in case anyone has any questions. We have some quiet audience here.
Yeah, so they're ready to.
Yeah. Okay. My suggestion is this. So since the presentation itself is very scientific, I will ask for the paper itself, if that's possible. Can you send me the paper itself, so I can pass around the papers for the students to read?
Yeah.
Okay, I'll appreciate that. I think going back to the paper would probably clarify some of the questions. It's 45 minutes with a lot of information to digest. It's kind of hard. Okay.
Yeah, the
yeah.
paper is in JAX, so I will send you the link.
Yeah, I appreciate that. Okay.
Okay.
All right. So
Great,
thank you very
then.
much,
Thank you
Dr. Ma,
all.
for giving
Yeah,
us.
I guess we'll keep in
deep dive.
touch. If you next time visit College Station, do let me know.
Yes, I will.
Yeah, so sometime I probably will travel to San Antonio and then we'll
Yeah.
catch up.
Yeah, let's catch up.
Okay.
All right. Okay, thank you again.
Bye.
Bye-bye.